Okay. Hello everyone. Welcome to the last lecture for my part of the course. And again, it's a very big thank you from my end to all of you for turning up every day, like for every lecture and listening to what I have to speak. So it has been really enriching and great learning experience for me also. So thanks. Okay.
Thank
So
you.
no worries, no worries. Thank you. Yeah. So let's begin. So we will begin by a small recap of where we ended last time. So we said that in the chiral basis that we were looking at things. So where let me see what was gamma 0 and gamma I in this basis, because we will also discuss another basis today. So in this basis, gamma 0 was like 0, identity, identity, and 0. And gamma I was 0, sigma I minus sigma I is 0. Yes, another thing, before I go into the detail. So for today, as I was saying yesterday, that I would require 30 more minutes. So if it's okay, I will uh, go till what's that, 9:40 in Bangladesh time. Yeah. So I hope that's fine. Okay, just for today, because I think there's a lot to cover. So we will see. Okay, so this was the chiral basis that we defined, and we wanted to do computation. We did some computations in this basis. It's also called the Weil basis. We will see why it's called the Weil basis. And in this basis, we said that the uh, rotation and the boost spinner representations looked something like this. So they were essentially block diagonal, and boost was like this. Again, block diagonal, but with opposite signs. And because of this, when you act these matrices on the Dirac spinner psi, you can see that the psi can be written as a two component object, which we will denote u plus and u minus, because of the block diagonal structure of the above matrices. And you will see that u plus will go to will transform with a plus sign under the rotations. So u plus minus both, but the boosts, so this is under rotation, but under boosts, they will transform under a minus sign. Okay. So that have a spin flip for that. Uh, so that's why u plus and u minus both transform with a like the same way in rotation, but they transform in opposite way under boosts. Okay. U plus and u minus. So here they transform same way. So they have the same sign plus here, but here it depends on whether you are transforming u plus or u minus. And uh, these objects that psi could be split into decomposed into two objects, two component objects. So remember, psi was a column vector of four, like four components. So u plus will have two components and u minus will have two components. So these u plus and u minus are what are called Weil spinners. And that's why you see all of this was basis dependent. This basis that we took that allowed us to write these rotations and boosts as block diagonal matrices. And hence from their action, we got this two component, like two component blocks. And so this was a very basic basis specific things, and hence these are called like the Weil basis, because they give rise to these wild spinors. But in a different basis, this won't be the case. We will see another basis today. And now, if you just write down the uh, Dirac Lagrangian, which was given like this, uh, I gamma mu del mu minus m psi. So here let me introduce a notation. So whenever you will have gamma mu, let's say another vector a mu, we will write it as a slash like this. So gamma mu del mu will be like uh, the differential operator with a slash. Okay. So in other words, you can write this as psi bar I del slash minus m psi. So that's a notation, just a notation for simplicity. So if you take this and you plug in psi as u plus u minus, and then take the Dirac action to 0, which we did already. So you can directly look at the equation of motion with this input. What you will get is the equation of motion for the plus component, plus wild spinner is this, and the equation of motion for the minus is this. Okay, where we have introduced a notation again to write things compactly, that sigma mu is 1 comma sigma I. So sigma I is a Pauli matrices, and sigma bar mu is 1 minus sigma I. So with this you can easily show uh, that. So you take the Dirac equation and plug this two component spinor representation of the Dirac spinor, and you get the equation of motion for each two component, u plus and u minus. Now we will see why they are called u plus and u minus and how it is related to chirality or handedness. So, so before that, let us discuss very briefly degrees of freedom of the Dirac equation. So, what are the of the Dirac spinor? Sorry. So, degrees of freedom of the Dirac spinor. So, note that psi has 4 components. So that means, and it's a complex field, so it has 8 real components. And in a physical system, the way you compute uh, real degrees of freedom is essentially half the degrees of freedom in the phase space. Okay. So what do I mean by that? Let's say you looked at any classical mechanics particle. In that case, you have the concept of a phase space where the coordinates are generalized coordinates and the canonical momenta qa and pa. And note that this pa was proportional to qa dot, and these things were independent of each other. The position and the velocity were independent. That's why when you are solving a second order equation in classical mechanics, you had to give two sets of information as an initial value problem, the position and momentum of a particle, or position and velocity. So what are the degrees of freedom here? Let's say, if you're looking in 3 dimensions, then Q has 3 components, P has 3 components. So in 3D, it has 6 components in total, 6 real components. But we said that, but you know that the actual degree of freedom of the system was just the 3 independent directions. So that's 3, which is half the number of degrees of freedom in the phase space. Okay, that's how the counting goes. So here we can do similar thing. So for that, let us define the canonical momenta for psi, and let's denote it by pi. And that, if you compute from the Dirac Lagrangian, it will turn out to be I psi dagger. So the phase space now will be psi and psi dagger. Okay. But you see, this psi dagger doesn't depend on psi dot. Okay. So hence, in the phase space, all the counting of degrees of freedom come from psi only, because the momentum here is just the conjugate of psi. So it's not like related to the psi dot or the velocity, and hence it's not an independent quantity that way. So the degrees of freedom in phase space for the Dirac spinner, because the canonical momenta is just the conjugate field, that just means this becomes that this dictates that there are 8 real components in the phase space, which essentially are the number of independent components in psi. So that means the real degrees of freedom of the system, which is described by psi, will be 4. Okay. And yes. So what are these 4 levels? Now you see, as we will see today, that psi was a complex object, was a complex field, and it had 4 components. Now we are seeing that the real degrees of freedom that it has is 4. So psi, when quantized, as we will see today, it will give rise to particles and antiparticles, just like in the complex scalar field case. So in both of these cases, there will be something called a spin, and there will be spin 1 and 2. So these are just levels. And similarly here, there will be spin 1 and 2. Okay. So all total, you have exactly 4 uh, independent degrees of freedom for the system. So that degrees of freedom is what we are calling spin. But later we will see that this is indeed the spin half up and down for the particle and the spin half up and down for the antiparticle. So hence you have, so that matches this counting, and that counting comes from seeing how many degrees of freedom the spinner field has. And yes, and one thing I must say here, that if this feels weird that the conjugate momenta for a field is just the uh, conjugate of the field itself and not something like psi dot, then recall that this happened because the Dirac Lagrangian was first order in fields in the field psi, unlike the Klein Gordon where you have, so recall that the Dirac Lagrangian was proportional to like a quantity like this, and that was it. But a complex scalar, on the other hand, had uh, like second order terms like this. Okay. So though it's a function of a first order field, but there were terms which were like quadratic in that first order. So because of that, here the conjugate momenta was like phi dot, but here the conjugate momenta is just psi dagger. Okay. So this is again built into the way the Dirac equation is constructed, that it's linear. Okay. Okay. So with that aside, so now we understand that the spinner field has 4 real degrees of freedom, and they will be the spins of the particles and antiparticles. Now let's move on to chirality or handedness, that and try to understand these U plus minus better. Chirality or handedness and these U plus minus, okay, that we introduce the Weyl spinners. So for this, note that we introduced another gamma matrix yesterday very briefly, which was like this. And you can show that gamma mu commutes with anti-commutes with all the other matrices, and gamma 5 square uh, goes to identity. And those of you who would have noticed the Clifford algebra quite closely yesterday, you might see that these were exactly also the properties satisfied by gamma 0. Remember that gamma I squared to minus the identity, but gamma 0 squared to identity, and the anti-commutation also was satisfied by gamma 0. So that means, in some sense, gamma 5 and gamma 0 are playing the same role. And this is where we introduced another basis, which is called a Dirac basis. And in that basis, the gamma I are the same, but gamma 0 becomes gamma 5 and vice versa. Okay. So let's say you are in the while basis. So in that basis, you will have uh, gamma 0, gamma I. So this is the while which we were discussing. If you go to the Dirac, the gamma 0 becomes the gamma 5 of while. Let me write it while for that. So this is gamma 5 of while, and this is just this. So this will be called the Dirac basis. So essentially what happens is the gamma 5 of Dirac gets identified with the, sorry, gamma 0 of Dirac get identified with the gamma 5 of while. So this kind of a basis transformation takes you from one basis to another where only this thing changes. And you can actually show that whenever in matrices we talk about transformation of basis, we say that they should be related by a symmetry transformation. So the symmetry transformation here, sorry, by a similarity transformation. So a similarity transformation here is invoked by the following matrix, and you can check this explicitly. So identity matrix 2 cross 2 minus of identity, identity, and identity. So it means that if you have the while basis, this is S inverse, the Dirac basis, and S. So that S is this. So you can explicitly check that the two bases are related this way. But operationally, what it means is you just flip the gamma 0 to gamma 5 and gamma 5 to gamma 0, depending on like if you go from one basis to another. So now let's see what this gamma 5. Uh, so again, just let us remain in the while basis for now. But this was a good point to introduce. So I introduced the Dirac basis. But now let's go back to the while basis. And because of these properties of gamma 5, you can easily show that this infinitesimal S mu nu, they will commute with the gamma 5. And so it means this gamma 5 is like a scalar under rotations and boosts, because they came about exponentiating this S, right? So again, this is exactly similar to how gamma 0 was there, and that helped us to construct the Dirac conjugate field. Okay. Uh, then the next thing is, with this we can define what are called projection operators using gamma, and they are defined like this. And I will say why the convention plus minus comes from. Okay, so the identity plus minus gamma 5. Uh, so in order to see that they are actually projections, you have to show that they satisfy these properties. P plus minus square is P plus minus, and P plus P minus is 0 as matrices. Okay, so this is just a simple matrix computation. So if you do that, then that's what the definition of a projector is. So they project to orthogonal spaces, and that's where this relation holds. And this is just the definition of a projector, which is an idempotent matrix. Okay. So you can now show with the definitions that if you take P plus minus and you act it with the finite Lorentz transformation in the spinor representation, then it actually gives you 0. Okay. Uh, and if you take, if you look at the Dirac field, then if you act P plus minus on psi, you get U plus minus. Okay. So what it takes is, what this projection operator does is takes the full Dirac field, which was U plus and U minus. And if you act it with P plus, it projects it only to U plus. If you act it with P minus, you get U minus. Okay. So, but remember that this is done in the while basis. However, this equation is basis independent. Also, these things, because they just follow from the Clifford algebra identities, and hence even this equation is basis independent. Okay, so so why did we do that? Is because we first started by saying that there is this while basis where the Dirac spinor decomposes into two while 2 cross 2 matrices. But that decomposition, one could argue, was a basis dependent decomposition, and that's true. So we want, and from that we argued that this property of reducibility. So this property is called reducible property of a representation. Yes, this property, that writing the Dirac 4 cross 4 is 2 cross 2 and 2 cross 2. So so this is this means that the representation is reducible, this representation S. And so we wanted to have a consistency check that if we do not use any basis, we still get that kind of a property. And that comes essentially from here, because if this is true, then it said that this representation, so this is the definition of reducible representations, which means that if you pick a basis, then there exists a basis where S of lambda is block diagonal. Okay. So at first we saw this explicitly in the while basis, and now I am giving you what's the rigorous definition of representation being reducible, and it means that you will be able to find projection operators that satisfies these commutation relations. So if this feels too abstract, forget about all this. Just remember that in the while basis, we can write the Dirac as two different objects, and that came because this S lambda for rotation and boosts, which are the generators of the group, as you know, they were block diagonal, and hence it split. So, and you can show that all these projection operators do is take the psi and map it to U plus or U minus. And but if you want to do it in a basis independent way, this kind of two component thing, then psi, then the way to decompose psi is like this. So you define what is psi plus as its projection by the P plus, and psi minus as the projection by the P minus. And in the while basis, as we saw, this exactly boils down to U plus and U minus. Okay. But in a general basis, this is how you can get the chiral. So this is called the chiral projections. We will shortly discuss what is chiral here. The chiral projections of psi. Okay, in a basis independent way. So now we will see why this thing plus minus is appearing. Why I'm calling chiral or left-handed or right-handed. We will see this now. Just one more thing I should mention, that in this while basis gamma 5, you can write it as this. Okay, these are identity 2 cross 2 matrices. Now, for that, to understand handedness, let us discuss two concepts. So first we will discuss parity. Okay, and then there will be a second thing called helicity. Okay, we will do one by one. So first is parity. So now recall that all these discussions of finding a spinor representations and everything was done around this group, which was the subgroup of Lorentz group, but the proper orthochronous transformations. And the reason we did that was because we could infinitesimally get away from the identity and do an infinitesimal transformations on the fields. Okay. Yes, exactly. Here gamma 5 is in the while basis, right? So now recall that we want to extend this study to what happens when you include also parity. So this thing didn't contain parity. So if I denote parity by lambda p, so this didn't contain parity, but now we want to look at what happens when we include parity and try to understand its action on the spinor field. So recall that what does parity do is it takes t and x to t and minus x. Doesn't spinor field include, sorry, there was a question, group as an internal symmetry. Sorry, I don't understand your question. Spinor field as unitary group.
So I said that you said that all these things is orthogonal group. That's mean it explains the external symmetry. So I said that spinor field also in means internal symmetry like spin symmetry or spin rotation. So I'm asking that is there anything like um,
No,
unitary group?
no, no,
Unitary group.
I didn't understand your question at all. What do you mean by external symmetries and internal symmetries?
External symmetry means that space-time translation,
No, no,
and internal.
there's space-time symmetries. Yes.
Yes, and uh, also
And
that for unitary rotation, so it's all the unitary group. So you
yeah.
said that this is orthogonal group. So I'm asking that is there anything like unitary group? Because there in spinor field there is also spin,
No,
spin
see,
rotation.
by definition, every orthogonal group is an unitary group, right? Because what is an orthogonal matrix? U O dagger O is identity. What is an unitary matrix? U dagger U is identity. Sorry, O transpose O is identity. But if you are just in, but orthogonal groups, orthogonal matrices are defined for real entries. So this boils to this. So every orthogonal group by default preserves unitarity.
Okay.
Okay. Okay. So I think the confusion is coming from that I said SO3. But yeah, this forget about SO plus 1 3. This is just a notation. All I'm saying that we looked at infinitesimal Lorentz transformations till now. Let us look at parity, which is not an infinitesimal transformation because it just flips the sign of x, the space vector. Okay. Now, recall that yesterday we proved that psi bar gamma mu psi was a Lorentz vector and it transformed like this, right? So under a transformation, it transformed like this: lambda mu nu gamma nu psi under a Lorentz transformation. And in order to prove this, we had to prove this equation first. If you go back and see the lecture notes, you will see that this was the equation that was crucial in showing that this is a transformation that happens under a Lorentz transformation on the spinners. This kind of a spinner bilinear. Okay. So, and we concluded that this was a Lorentz vector. So now we want to argue something similar for parity. Okay. So in order to preserve parity, so previously this lambda was just any infinitesimal Lorentz transformation, like rotation and boost. But now we also want to do the same for parity. So if we do that, so we should have uh, this kind of a transformation for parity also, so that you get lambda but for parity and gamma nu. So this p is not an index, this whole thing is the parity matrix. In other words, this lambda p mu nu is, if you remember, the parity matrix, which is diagonal plus 1 minus 1 minus 1 and minus 1, because all it does is flips the x to minus x. That's why you have minuses for the x and plus for the t. So, so this is the equation that we want to look at, and we want to see what kind of a S lambda satisfies this. And you can take a guess. So the guess is, let's try with S lambda P equals gamma 0. Okay. Now if you, sorry, there's a question. No, gamma mu itself is not a vector, but only when it is sandwiched. But that's a good question. I will answer this in more detail later. And that follows from the fact that only when you sandwich these things like this, then only you have the correct, because you see psi bar, they all transform. And the way they all transform together makes the whole thing as a vector. So that is necessary. But we will see like other transformations and in more detail. Yes. So as I was saying, you take S lambda P as gamma 0. This is like a guess, and try solving for this equation and see if it holds. That is this equation. Uh, this equation holds. And from the properties of the Clifford identities, you can show that indeed this works out. Okay, so that's again a very simple exercise. So I can give you a hint that you first do for the time components and then do for the space components. And if you do that, you will see that this works out. And here is also a tip that whenever you want to satisfy identities like this, if it doesn't work out immediately, just separate space and time and do one by one, it will work out. So you can show that gamma 0 actually is satisfied by this. So this means that under parity, now psi will transform under this parity as S of lambda p psi, which as we argued is gamma 0 psi. But now let us write down the arguments also. So under parity, it will transform as gamma 0 psi, but the argument will also flip sign because that's what parity does. Okay. So that's the transformation rule for parity on the Dirac spinner. And now let's see what it does. So now if we expand this, so it becomes u plus and u minus. And if you recall, in the while basis, gamma 0 was given like this, u plus u minus, and then you can see that you get u minus u plus. Okay. So this means, you see, under parity, u plus minus go to u minus plus. And this is where the concept of handedness is built into this whole construction. Is, you see, a right-handed coordinate system is, let's say, what's a right-handed coordinate system? It's like you have an y here, you have an x here, and this is like the z. But imagine the z is pointing out of my iPad, so it's pointing up. So that's why when you do I cap cross j cap, you get k cap. Okay. So essentially, you take your right hand, you start from the x-axis, you turn towards the y-axis, and the thumb points in that direction. But one could also have taken a left-handed coordinate system, which is, so this is right. You could also have taken a left-handed, which is like x here, y here, but the z goes down. Okay. So it points into my iPad now. So now if you take X and Y, you turn your hand the way you want to do the uh, cross product, you will get K downwards. And you see, parity essentially exchanges. So let's say parity was acting on this Z here. So parity flips, because parity flips the space directions, it leads to a change from a right-handed coordinate system to a left-handed coordinate system. Okay. Um, and because of that, you see that the action of parity also on these while spinners flips them to u plus to u minus. So this means u plus naturally is defined in the right-handed system and u minus in the left-handed system, because that's what parity does to coordinate systems. And this is why we were calling them that u plus is, let's say, right-handed and u minus is left-handed. So in some textbooks, you will see that u plus is written as UR and U minus is written as U left. And the idea is because parity flips the handedness, and in this explicit computation, we saw that under parity, they map into each other. Okay. So now we will, yes. So now you can do an exercise, which is that if, let's say, if, and then we will discuss more about this handedness, but let's first look at this exercise. So let's say if psi satisfies the Dirac equation, then you can show that we said that when parity acts on psi, then we get gamma 0 psi. So but the x becomes minus x here. So you can show that gamma 0 psi t of minus x also satisfies the Dirac equation. Okay. So here we see a thing, which is that the Dirac equation, this means uh, is parity invariant, okay? Because under parity, the equation remains the same. And if psi satisfies, then gamma 0 psi also satisfies. And yes, so that's one thing. And note that this is our first encounter of a discrete Lorentz transformation and an equation of motion which remains the same under that. Okay. Now let us come back to the question that was asked on the chat regarding vectors. So now let us see what more general things that we can do apart from vectors. So as I said that this thing was a vector, but not just gamma mu itself. So now let's see what other things we can build. So we already have had a scalar. So this was a scalar. So note that under parity, scalars will just remain like that. So if these come with, so here x is the 3 vector x, but I'll not write the vector on top. And they just map to themselves with the space position now reflected. Now you can show that for vectors, that is psi bar gamma 0 psi x and x, that maps to psi bar gamma 0 psi with minus x. And for the time parts, this maps to minus of, so let me explicitly show you this once and then you can do it. So it transforms like psi bar minus x gamma 0, then gamma I, and then a gamma 0 and psi of minus x. Okay, because this is the parity for the psi, and this is the parity transformation for psi x. So if you now anti-commute gamma 0 and gamma I, you will see that you will pick up a minus sign, mm, gamma I psi of minus x. Okay, so it means that this is exactly how parity transforms, right? So because remember, parity for coordinate vectors was t and minus x. So the time remained invariant, but the space flipped sign. Similarly, for this vector, the time component comes with a plus sign, but the space component comes with a minus sign. So the question that was asked, you see again this pair is actually a vector. Just as coordinate vectors transform, it under parity, it also transforms in the same way under parity. Now you can now note that there was an exercise last time, that if you take this S mu nu that we have been talking about, then you can show that this transforms like an antisymmetric rank 2 tensor. Okay. And now, but notice that we have another thing, which is this gamma 5, and we had argued that this was also a Lorentz scalar. And we secretly know that this gamma 5 is nothing but gamma 0 in a different basis. So they must have the same properties. So with this, you can construct two more objects. So psi bar gamma 5 psi and psi bar gamma 5 gamma mu psi. Okay. And you can show that psi bar gamma 5 psi transforms under parity as minus psi bar gamma 5 psi. So these were x's and now these are minus x's. Note that this is different from how scalars transform. So scalar, remember, transform with a plus sign, minus x and x. So this comes with a phase of a minus sign. So hence this is dubbed as a pseudo scalar. Okay. Why pseudo? Because it doesn't have any index here, no index. But still it comes with exactly the opposite sign of a scalar under parity. So that's why this is a pseudo scalar. And if you looked at the other guy, so gamma 5, so let's again break it to space and time components. So the time will now come with a minus sign. Again, these are x and these are minus x. Remember that. If I miss out, then just remember that. And for the spatial components, they come with a plus sign. Okay, so this is opposite to how uh, the vector transformed in the under parity, and also how the coordinate vector transforms. And hence this is called, it's, you can call it a pseudo vector, just like the naming, but it's also called an axial vector. Okay, or if you like, you can call it the pseudo vector. But in textbooks, you will find this as the nomenclature. And the reason is the time and space, they transform oppositely to how an actual vector transforms, or how the coordinate vector transforms under parity. So now let us do a counting. So all of these quantities are called Dirac bilinears. And why Dirac bilinears? Because notice that what did we have? We had a scalar, we had a vector. So all of these were sandwiched between two Dirac spinors. So the spinor and its conjugate, Dirac conjugate. So that's why the name bilinear, and made out of Dirac fields. Okay. So hence these are called Dirac bilinears. And what did we
So
have?
it's that plus x and the last equation, the subscript, minus x to
That's a
plus
minus.
x,
Yeah.
minus, okay.
Yeah, just the usual one. Okay, it's a typo. Okay, thank you. So we had these two. We had this guy. Then we introduced the gamma 5. And finally, we also had this. Okay. And now let us count how many are there. So this is just one. This is because of the index is 4. This is antisymmetric, as you know, in 4 dimension, it's 6. This is 1 and this is 4. So the net will come out to be 16. Okay. And that's exactly what the Dirac, the total number of real like components of a Dirac thing is, because you have psi and psi bar. Okay. So for a 4 component Dirac spinor, you will have these many independent count. Okay. So this matches the count, and you can now write down any Lagrangian that you want to write. So we wrote down the simplest one, which was like I gamma mu del mu minus m psi and psi bar, and that only involved these two bilinears, this one and this one, the scalar bilinear and the vector bilinear. Okay, and yes, so but that was the simplest one that we wrote down, and that gave us the Dirac equation. We will see that even the simplest looking equation will give us so many leverage when we quantize it. But now, if you want to write down more terms here, like interaction terms, let's say, you can add a chiral piece like this. This will be called a chiral piece because, as we saw in detail, that under parity it behaves little weird, not like the scalar case, and it has these properties that it takes you from one right-handed system to a left-handed system and all these kind of things. So so those kind of interactions you can add on top of this. But these 1 2 3 4 5, these five quantities are the independent quantities that you can take to construct any Lagrangian or an action with Dirac spinor. Okay, the spinor fields that we have been talking about. And as you see, there are 16 of them. And that exactly matches the components of psi and psi bar. Okay, so one is a 4 component, means 8 real components. Psi bar is again 4 components, means 8 real components. So all total you have 16 components. We call them bilinear because we are sandwiching them as psi and psi bar. uh, because you see, like, if you look at this guy, so it's sandwiched between psi bar and psi. So that motivates the name of bilinear. Okay. I'm forgetting there is some, I think, some justification also that it's bilinear in the fields, but like an expression is bilinear if it is linear in each variable. But let's not go into that. You can just imagine that because there is psi bar sandwiching in each term, that's why these are called Dirac bilinears. Okay. Uh,
And you said with the five entities, we can construct what? We can construct any theory?
you can construct any relativistic theory with spinors. Okay. For instance, we
Okay.
constructed this theory that came to be known as the Dirac theory with only these two spinors.
Right.
And you could have also added other things, but as we discussed, those will be higher interactions, like different interactions, like chiral interactions and other kind of stuff.
Okay. Thank you.
Yeah. Yeah. For instance, like another example could be you could take this psi bar s mu nu psi. So this is a nice, um, nicely transforming object, and you can contract it with, because of the antisymmetry, another antisymmetric object a mu nu, and this could be some term in your Lagrangian, Dirac Lagrangian, but now also involves this extra interaction kind of term. So all of these kind of things you can do. The idea is that you have to choose uh, uh, these five as the basis if you want to construct your Lagrangian, and the simplest one is including these two, because you want a derivative operation acting, so you need a vector, and obviously scalar is even more simpler than a vector. So that minimal ingredient gave us the Dirac equation. Okay. So now let's move on to a bit more about helicity, and but this will, they have the alpha index. Yes, they exactly have the alpha index hidden. So I'm just writing psi, but it means psi alpha. Okay. Uh, okay. Now, so there is something called an helicity. So I'll briefly discuss it, but there is an exercise in the notes that if you do, it will be illuminating into this right-handed, left-handed thing. So helicity is defined as this matrix. So the helicity operator is this matrix. Uh, the momentum unit vector times the Dirac Pauli matrices, which, as you know from your quantum mechanics course, are got to do with the spin quantum number. So essentially, the definition of helicity is when you take the spin operator, which is the sigma here, and project it along momentum. Okay. So when you do that, what you get is helicity, and the proper definition is this matrix. So P is the momentum, sigma is the spin operator. So you computing the dot product is essentially giving you what is the projection of the spin along the momentum. And this is an important quantity, because you see that when we defined what is called a spin, we had this expression in the classical field theory language, that and then there was this r cross p piece, okay, which was like x rho del sigma and anti-symmetrized. So, and then what was the strategy? The strategy was to get the intrinsic piece. We had to put the momentum to zero, or and that led to vanishing of this guy, and that gave us the intrinsic M, which was identified later in the quantum theory as spin. Okay. So Q is the quantum map, if you like. So when you quantized, this M was identified with spin. Now, here, you see that so this is fine when you are dealing with spin of massive particles. Okay. So when you're dealing with massive particles, spin makes sense because there always exists a frame, which is the frame in which the particle is, where you can have its momentum to zero, right? So which is called the rest frame of the particle. So because it's a massive particle, you can do that. But for massless particles, as you know, because they being massless by relativity, they're always traveling at the speed of light. So there doesn't exist a nice notion of rest frame. Okay. And it becomes weird. Okay. And because of that, this way of defining the spin of a particle, which is essentially computing this operator and then going to the going to the quantum picture and then setting the momentum to zero, which is like going to the rest frame, doesn't work out because there doesn't exist a nice rest frame for a massless particle. It's ill-defined. But this kind of an object still will work because the massless particle still has a momentum, which is like just the MC part of it. And you can take the spin operator and then act it on the momentum to get the helicity. So, in the strictest sense, spin, when people say spin of massless particles, all they mean is this helicity. Okay. Because as we argued, otherwise it's not properly defined. Now, there is an exercise that you take these Dirac spinners and you express them as like this as plane wave solutions. Okay, sorry, these are uh, four vector inner product. So you express them as plane wave solutions. So what this means is this is u plus and u minus, and there's a plane wave attached to it, and then you put it in the Dirac equation, and then so put this in Dirac's equation of motion, and you set m to 0. Okay, when you do that, you so you take Dirac equation, substitute this, and put m to 0. When you do that, you can show that these u plus minus are eigenvectors of this helicity matrix that we constructed. Okay, and then the next thing to show is next thing to find is you will see that they have eigenvalues as plus and minus half. Okay, so in some sense we are already seeing the structure of spin emerging, but you see in this there was a key thing that I had to set m to 0. And why that m to 0 made sense? Because only when we set m to 0, spin and helicity, like the spin for the massless is nothing but its helicity. And hence, only when you set m to 0, these u plus minus become the eigenvectors of this helicity operator, and they give you eigenvalues as plus minus half. Okay. And as we have argued, they have something got to do with having a left-handed system or a right-handed system, which is related by parity. Okay. So if you do this exercise, again, very simple, you take this, act with the Dirac equation, and use the Dirac equation to prove that they are indeed the eigenvalues of this operator. And once you, eigenvector of the operator, once you have them, then calculate eigenvalues as usually you do. Okay. Now let's move on to symmetries of the Dirac Lagrangian. So what are the symmetry and conserved currents? Because we have written the Lagrangian since yesterday, but we haven't yet discussed this part. So for that, note that under translation, just like in Noether's procedure, we have done it. Under translation, this the spinner transforms like this, where epsilon is, let's say, the translation thing, parameter. So you can then write down the stress tensor using exactly the Noether's procedure as this quantity. Okay. So I won't go through the details here because we did it for the scalar field quite detail, and this is exactly that. But now note that we had this concept that on shell we had that del mu t mu nu was 0. So which was essentially saying using equations of motion. So we had this thing for the conservation of currents using the Noether's procedure. So we always said that they were conserved on shell, which meant that the equation of motions have to be satisfied. Now recall that the Dirac equation was just this, right? Mm, I gamma mu del mu minus m psi is 0. Okay, so this was the Dirac equation of motion. But you see that if you just multiply psi bar on this, then you get the Dirac Lagrangian. Okay, because the Dirac Lagrangian was just psi bar I gamma mu del mu minus m psi. So it means that on shell, the Dirac Lagrangian is just 0. So which is quite new, because in the complex scalar field case this didn't happen. But that again is tied to the fact that the Dirac Lagrangian is first order in fields. So it was a linear equation, linear differential equation. So if you do that, then you can put this to 0, because these currents and their conservation only makes sense when their things are on shell. So that simplification then tells us that T mu nu is just this guy. Okay. With this, now you can do various things and sorry, before that, you can see that this has nice transformation property, because we know psi bar gamma mu psi transforms like a vector, Lorentz vector, and del nu by definition transforms like a Lorentz vector. So this is a nice rank 2 tensor. So with that out of the way, you can compute the total energy in the usual way, and you will get something like this: psi dagger gamma 0 minus I gamma I del I plus m psi. Again, these are trivial manipulations, so you substitute the 0 0 component and you get this to be the energy. We will use it today when we go to the quantum theory and write it in terms of ladder operators. So this expression will be useful then. So now this is under translation. Now for rotations and boosts, again you can do something similar. Uh, so let's say you look at an infinitesimal Lorentz transformation, capital omega. So that's how the coordinate transforms. And this is how the spinor will transform. Again, the way to do this is expand the exponential, if you remember, and ignore second order terms. Okay. So if you do that, you'll be able to show that infinitesimally, this is how the spinor will transform. And here these omega mu news are the thing that are exponentiated, or in other words, these are these generators, the Lorentz generators that act on the vectors. Okay. Coordinate vectors. And now using the explicit form of this m rho. So remember, this was written like in terms of etas and deltas. You can show that del psi alpha is indeed can be written compactly like this. Okay. So I'm not doing each step, because it should be clear by now that you just have to expand the exponentials, treat that as a infinitesimal symmetry or Lorentz transformation in this case, and then equate term by term. And from this, the current that you will get will be very similar to what we got in the scalar field case. So remember there, the current associated to boosts and rotations was only this. But now you see that because of this S guy appearing everywhere, we will also have its appearance here. Okay. This S that was built out of the Clifford generators. So this extra piece was absent in the scalar case, because obviously a scalar is not a spinor. So that spinor properties, as we have argued so much, was captured by this S. So that's why under rotations and boosts, because spinor transform in a way that we have already discussed, that you will get an extra piece like this. Okay. And when you will do QED, you will also get something like that, but not for a spinor part, but for the vector index there. And you will see what that comes about to. Okay. So now the usual thing would be that when you quantize the theory, this will turn out to be an operator. And then if you look at uh, the components of it, like J0 rho sigma, and just like as you had done for the scalar field case, if you act it on a one particle state, you will get it to be spin half or minus half depending on the particle that you are acting it on or the excitation you are acting it on. Uh, so that will confirm to you that these things that we are constructing, these spinor fields, their excitations is giving half as the spin. We already saw this briefly for the massless case when you will compute these eigenvalues, but now for massive or in general, you can see that they will give half, which was 0 for the scalar case. Okay. Okay. So that out of the way, now let us discuss some internal symmetries. So which are symmetries that are not space-time symmetries, or they don't depend on space-time symmetries. So you can see that under so there are two of them under this transformation. The Dirac Lagrangian is invariant. Sorry, and you can construct the current from it as something like this, and the V is because this is actually a vector, as we have seen. So this V stands for the fact that this is a vector, as we have seen explicitly. So this is the current, and now you can use the Dirac equation to show that this is indeed conserved. Okay. And you can compute its charge, which will be T3x psi bar gamma 0 psi, which, as you know, is just T3x, the Hermitian conjugate psi, because this has a gamma 0 built into it. Okay, recall this was psi 0, psi dagger gamma 0. Now, when people talk about charge of the electron or proton or whatnot, it is this charge that is being computed, this Q. Okay, because this gives the electric charge or the fermion number, because this counts the number of fermions you have in your theory. So if you like, it is the electric charge or the fermion number, how many fermions are there. And yeah, so this is exactly what you measure in the lab. However, there is a small caveat. I won't go into that, but I have written something in the lecture notes much before on that. The caveat is that when you will do QED, there you will see that this psi that was translating as e to the power minus I alpha psi, here this was a global symmetry in the sense that it didn't depend on a space-time. Uh, but in QED, you will see that you will promote this alpha to depend on space-time, and you will encounter what is called a gauge symmetry. Okay. And then you will study many things about it. I won't talk in detail about this, but a gauge symmetry is actually not a symmetry, as you will see, because it's just a redundancy in your system. So then there it will become a bit confusing as to what's the meaning of a gauge charge then. Okay. So I have a discussion on like when we discuss Noether's theorem in that part of the lecture notes, where I have a little bit argued that even if you have a gauge symmetry and a gauge charge, like at infinity, you can have some imprints of that gauge symmetry. Okay, so these are just words for you now. I'm not explaining anything. But if you go through that section and when you read QED, it might give you some satisfaction. Okay, but we won't do this here. Now there is another symmetry, which is again a global symmetry, which is this guy. Okay, psi going to e to the power I alpha gamma 5 psi, and psi bar going to e to the power e to the power psi bar e to the power I alpha gamma 5. Okay, and can be derived from the first one, just noting the transformations of gamma 5 and gamma 0. Okay. So if you expand the exponentials again here, you can understand that this actually happens, and hence the psi bar transforms like this, and if psi transforms like this. And this is what is called an axial symmetry. And the reason being, because note that the current that you will get here will be psi bar gamma mu gamma 5 psi, which we called as an axial, or I said you can call it a pseudo vector. Okay. But you see, the problem of calling it pseudo vector was this would have become a pseudo symmetry, but actually this is a true symmetry. And hence people didn't call it pseudo vector, they called it axial vector, because it leads to a symmetry, which is called the axial symmetry. And then again, using the Dirac equations, you can show that del mu j mu a equals 2im psi bar gamma 5 psi. So note that it's actually not a symmetry of the Dirac Lagrangian or the Dirac action if m is not equal to 0. But if you put m equal to 0, then it turns out to be a symmetry. So this axial symmetry is a symmetry of the classical massless Dirac action or Dirac Lagrangian. Okay. So only after you set m to 0, you get it to be satisfied, to be a symmetry conserved. And now note that there is this word I sneakily put in the sentence, classical. Okay. Why did I say that? Because we have only been doing classical spinor field till now. We will quantize it like in 15 minutes. We'll start quantizing it in 15 minutes. So that's why this is fine. This is okay. This is correct. This statement is correct. But there is something more to this statement, and that is, this is again something you will probably learn in QED, but I will skip it for now. You will see that when you quantize the theory, then after that, if you compute this guy, like where now this is like an operator, you will find that this will not be equal to 0. Okay. Even in the massless case, like if you put m to 0, then when you quantize the theory, this will not be 0. And this is what is dubbed as an anomaly. Okay. So all it means is, like at the level we are talking right now, all it means is if there is a symmetry that is there in your classical action, upon quantization, if that symmetry breaks like this, then we say that we encountered an anomaly. Okay. Something is anomalous about the system. And I will not again go into any detail about anomalies, but just wanted to make a point clear. At least now you see that there is something like this weird happens when you quantize this. And more on this probably will be taught to you in the QED lectures, because there you will be able to actually derive this thing. But now we have no means to derive this. So again, forgive me for not going into detail here. But okay. Okay. Now we want to quantize. So in the remaining 1 hour, 20 minutes, we will understand the quantization. So for that, let's first look at plane wave solutions. So we already looked at some plane wave solutions when we gave that helicity exercise. So note that the Dirac equation was just this. I now forgot how did I denote the slash, maybe like this. Yeah. Yeah, so that was the Dirac equation. Now you can take a solution, a plane wave solution like this, psi x, which we did already in the helicity example, like this. Okay.
Don't we have psi bar on the left? That's the equation of motion.
Yes, this is equation of motion. That psi bar is Dirac action.
Lagrangian.
Yeah, yeah, action or Lagrangian, that, yeah, like this. So when you have the psi bar, this term is not 0, but as an equation of motion, this is 0, and that doesn't have the psi bar. And that you could see, right? If you just vary it with respect to psi bar, then you get this piece, which is the equation of motion. Yeah, the Euler-Lagrange equation of motion. Okay,
Yes.
so if you take this and if you plug it in the Dirac equation, when I say Dirac equation, I always mean the equation of motion. Okay, maybe that's was the confusing part. And now you can expand the gammas out, and you can show that this becomes like this in terms of the sigma matrices. So sigma mu and sigma mu bar, recall that we had introduced this notation today. And that is 0 from the Dirac equation. And again, let me write the notations. We did this in the beginning of the class, but for clarity, so this is what is meant by that. So you can write an equation like this, and hence this actually solves the Dirac equation. Okay, so this indeed solves the equation. Now you so these equations will be so these equations psi, let me denote it by plus. So psi I am denoting plus upstairs. The plus downstairs in some books is for the chirality, but the plus upstairs is because these solutions which come with a minus IPX are called positive frequency solutions. Okay, and to contrast them, there are negative frequency solutions which comes with, let me not write with red, which comes with the opposite plane wave basis. Okay, so plus IP dot X. And you can again show that they also satisfy the Dirac equation, but with a flip. So the exercise is that they satisfy this equation instead. Plus M Vp equals 0. And now recall that in the Dirac Lagrangian, there was this M appearing and not M square. And I briefly mentioned that M was not the mass parameter. This is just like a level. And the reason is this, because if you're looking at the other direction moving solutions, you get a plus M. But for the positive frequency solutions, you get a minus M. So hence you see there is a flip of M to minus M. So that's why M is not an observable or the mass. The observable will be M square, or the energy that you compute when you quantize the theory from the Hamiltonian density. So with these things out of the way, let's explicitly see what these solutions look like. So for this, so this is where we will work in the Dirac basis, because that's easier for getting these solutions. Okay, so one strategy that people do is, if you are looking at massive things, then you work in the Dirac basis. But if you are looking at massless things, then you look at the Weil basis. And the reason is, note that the Weil basis has this nice factoring into block diagonal as the Dirac spinner into Weil spinners. And when we put the Dirac equation mass to 0, we had this helicity operator coming in. So that's why it has an added advantage to deal with massless objects. But here, let's keep everything general. So that's why it's easier to find solutions in the Dirac basis. So, so in the Dirac basis, again, note that this whole equation was Lorentz invariant. So we can work in a particular frame and find the basis. So let's say we pick a rest frame, which is where the momentum vector is just this, the spatial momenta are 0 because it's the rest frame. And in this, the basis, the Dirac equation becomes, again, you substitute the momenta and the gamma matrices. So this is now a 4 cross 4 identity matrix acting on P, and that you can simplify to a 2 cross 2 identity block, and again P. And then you will see that the solutions that you get two independent solutions, and they are UP we'll call it 1, which is, so this root 2m is for just normalization, but the actual solution vector is 1 and all entries zeros. And there will be a up2, which is like 0 1 0 0. Okay. So these 1 and 2s are what labels the spin, or S for now, because only when you go to the quantum theory you see the spin. And the reason that there are two independent solutions was because, recall that the Dirac was made out of U plus and U minuses, and Dirac had four independent components, which means each of these will have 2 and 2. And so these 2 and 2 are these spins, 1 and 2. So one is this and one is this. And you can see these are linear independent vectors. Okay. Similarly, you can write the V's, which were the negative frequency solutions, as root 2m, and you could guess that they will fill out the lower ends of the components. You can explicitly show that this is from they solve the Dirac equation, and hence they're indeed solutions of the Dirac equation. So these will be my positive frequency and negative frequency solutions explicitly. So the full spinner is like u p of s times e to the power minus ipx, or vp of s times e to the power plus ipx. Okay. So this is like the positive part, the positive frequency part, and this was like the negative frequency part. And uh, and then let's see, what do I have to say here? Oh, okay. Yes. There's a question. Are those only for rest frame? Yeah. So yes, we computed their explicit form in this particular rest frame. So this kind of form is in this rest frame only. But you know how spinors transform under Lorentz transformation, so you can move to any general frame. So we took the rest frame, so just for simplicity, so that this is a simple matrix and I can write down its independent solution. But the equation, Dirac equation, is Lorentz invariant. So that's why its solutions will transform in a Lorentz covariant way. And you can find a similar U, let's say a U lambda in some transformed coordinate system. Okay. Yes. So yes, that's a good question. Uh, so the question is what happens for the massless case. So we will not deal with the massless case from here on, actually, because that will involve some complications. So we will only work in the case where m is not equal to 0. Okay. Because the massless part is something that will take a whole lecture in itself, because like it's a bit tricky. And the reason you could understand is this thing, right? First of all, we could solve this so easily because we could go to a rest frame like this, but for the massless case we cannot go to such a rest frame. So explicitly solving this becomes difficult. So I can give you some references later in the Slack, but I won't discuss it here. So we will only discuss the massive case from here on. But thanks for your question. I was forgetting about this. So we will only discuss the massive Dirac equation from here on. Yeah. Okay. Now let's yeah. So now in the remaining of the class, we will use some identities which whose derivations we will not do in the class. Neither I will write them in the lecture notes, but you can find them from David Tong's QFT notes. Okay. So they are not involved, they just take a bit of time. So we don't have much time. So we will just state them as identities for now. So the first one is uh, that if you take the Dirac conjugate P and you multiply it with the normal one, then you get an equation like this. And similarly for the V's, so V bar PS and VPR is minus 2M delta RS. And then there are some more identities, which is U dagger. So now what happens when you do the Hermitian conjugate? Because we had different kinds of conjugates, the Dirac and the Hermitian, remember? So the Hermitian conjugate gives you this thing, and then V dagger P bar R V P S equals 2P0 delta RS. Sorry if this is a bit dry, but we do need these identities when we will quantize the theory, and you can look them up for their proof. So the identities are there in the notes, but if you want to prove them, you have to consult Tong. That's the simplest reference that proves these things. And the machinery you need to prove them is already, we have discussed these things, like their matrices, and we know their transformations and all these kind of things. So we will be well equipped to understand the proof. And the final thing is summing over all spins now. So spin 1 and spin 2. And that gives you the Dirac operator, but in momentum space. And similarly, another one for the V, the negative frequency basis. Okay, so these are nothing but the Dirac equation, sorry, the Dirac operator uh, in the momentum space. Okay, because remember that P is del mu. Okay, so these are some identities which are called spinor identities, spinor completeness relations, inner product, outer product, things like this in the literature. And you can look up David Tong's QFT notes on the section on Dirac quantization, and there he will give you a derivation for these things. And but I think yeah, now that I recall, he works in the while basis, so he will give you a derivation in the while basis. Okay. But these relations, they hold they are basis independent. Okay, they're basis independent, so they also hold in Dirac basis. So if you're interested, you can look at the proof there. But now with this much in our arsenal, let's move on to quantizing and understanding where the this anti-commutator relation enters and all these things. Okay, I promised you last time that we will see that spin half, fermions, exchange of particles giving a minus sign, or anti-commuting things, all these are built into the structure of QFT. So we will see that. So that's the only rigorous thing that we will see. Rest all are either exercises or things like this that you would have to prove from Tong if you're interested. But for understanding sake, we will try and understand all that we can. Okay. So this is something that we will discuss rigorously now. So note that when we quantized the uh, complex scalar field, we said that the quantization amount to having relations like this, that phi x, phi y now as operators at equal time. So let's say t equals 0, they commute. Similarly, the momentums, they commute. Let's look at the real scalar field. That's easier. Otherwise, I'll have to put daggers here and there. And the phi x and the pi, the canonical momenta operator, they didn't commute. Okay. In fact, they satisfied this commutation relation. And we said that imposing this was what meant quantizing the theory. So now that means that the aim should be to have similar expressions, that psi alpha. Okay, recall first that the canonical momenta was just this psi dagger. So we should have, in this case, when we quantize spinors, these kind of relations. So the dagger is now momentum. Okay. So this is the momentum. So hence, this is the momentum relations, the canonical momenta relations. And the non-commuting important relation will be like this. Okay, so these are functions of x and functions of y, again at equal time. So delta alpha beta del 3x minus y. Okay, now let's see that. So normally one would imagine like this, right? That that's what Heisenberg taught us, that when you want to quantize the theory, you take the position and momentum fields, and then you promote them to operators, and then you enforce or impose these equal time canonical commutation relations. But we will see soon that if we do this, we will end up with a problem. Okay, and that problem will be tied to this fermions having spin half and all these things. Before that, because now we have studied the plane wave basis, so we can expand any Dirac spinner like this. So this EP I am writing was called omega p, and you have these operators now, these ladder operators, and u p of s e to the power I p dot x plus c p of s dagger v p of s e to the power minus I p dot x. Okay, and this again, you know that this is the whole solution of the Dirac equation, and it comes with a coefficient which we call ladder operators in the quantum theory. And similarly, you can write down psi dagger for the momentum, an expression like this, just taking the dagger of this. And now the claim is that if you impose these relations, let's call this star 35. So imposing star 35 or the equal time commutator relations, that gives you these relations between the ladder operators. Okay, B P R B Q S dagger. So this is expected from the complex scalar example, but what will not be expected, what we do to the C daggers. Okay, del 3 P minus Q. So this will be for the B operators, and for the C operators, we will get an equation like C P of R C Q of S dagger equals minus 2 pi Q delta RS delta 3 P minus Q. Okay. Now what is weird about this is, so normally in the complex scalar case, when we had annihilation and creation operators, they came with a plus sign. But now the usual way of defining annihilation and creation operators this way comes with a minus sign. Okay. And why does that happen? So the way to check this is if you take these two equations, these equations as they are given with a minus sign, different from the complex scalar case, opposite to the complex scalar case, and then plug them here, then yes, we will actually do this, if I remember correctly. Yes, so I will show you that only with this minus sign here, these these ladder operator commutators indeed give you star 35. In other words, the ladder operator commutation relations that is compatible with the equal time commutator relations between fields demands that there should be a plus sign here. Okay. But if that's the case, then we cannot say that the vacuum is this. Okay. Now this will no longer make sense. But what we can do is flip the sign here. So that will give me CQ S dagger CPR. So now that will have a plus sign. So we will say that let's try to fix this by saying that the vacuum is something that will be annihilated by the C daggers. Or in other words, these are the annihilation operators, and these will be the creation. Okay. Many of you might be objecting a bit now, but just hold on. We will see that even this will not work. Okay. So there will be a deep problem from here only, like starting from the equal time commutator relations. So we will see that no matter what we do, we will face a problem. Okay. So the first problem we faced was that this thing was opposite to the way in complex scalar field that works. And we said, okay, if that's opposite, let's just flip the job of the dagger and the non-dagger operators. Let's say that the dagger operator is creation and the non-dagger is annihilation. Sorry, the dagger is annihilation and the non-dagger is creation. But we will see that this again will lead to some problem. But first, let's see that this plus sign is important. So what we will do is we will take uh, these two equations and plug them in these expansions, and we will see that this comes out. This equal time commutator relation comes out. So for that, let's compute that. So psi x, psi dagger y, sum over the spins r and s, and now we will work in momentum space. So 2 pi 6, because these ladder operators are in momentum space. 1 by 2 EP EQ, and the commutator is between BP R and BQS. Okay, so that comes from here. So here there is this BPR, and I didn't write the psi bar, but let me just write it schematically, that this is like some factors, and then you will have a BS dagger and a CPS. Yes. So that's why you get B and B dagger commutator from the first line when you do psi and psi dagger on the left hand side. And then you will have UR, P. Again, this is a bit painful but straightforward. So do it taking your own sweet time, no rush. So at least once you should all do this very carefully, taking your own time. Okay. And then the other part is for the commutators between the C's. So that boils down to VRP, VSQ, and now with the opposite sign for the exponential, P dot X minus Q dot Y. Okay. And now we use, so here we can use the commutator relations that we are saying is compatible with the equal time commutator among the fields. So we plug in these things. So we are doing the reverse. Okay. So we are taking that somebody gave us these ladder operator commutator, and we want to show that we want to end up with these ones. So we're doing the reverse. So if you plug in them, you will pick up delta functions like this, P minus Q. So you can take away one integral, and doing that, you will end up with this. So D3P survives. Let's say I do the Q integral, 1 by 2 EP, because now P is Q. You get US P, US dagger P, and sorry, there were some daggers here. Yeah, I forgot. There's a dagger here and there's a dagger here. And then e power I P dot X minus Y plus VSP VS dagger P e to the power minus I P dot X minus Y. Okay. Now at this point, you see that there's a sum here. Now recall there was a spinner identity S1 to 2, U and U bar was given like P plus M, these Dirac operators, and for the V bar, it was P bar minus M. So because of this, now we can use them here, okay? Because we can imagine that you can write down. What we have above is something like this. You can write it as USP gamma 0 square US dagger P. And now you know that since gamma 0 square is 1, you can do this. So you have 1 gamma 0 times, actually, let's do this here. So gamma 0 square. And now you can use the identity for defining the Dirac conjugate. And you're left with 1 gamma 0. And now here you can use these spin sums, okay? So you can go from a Hermitian conjugate to a Dirac conjugate, recall, by multiplying a gamma 0 and using that gamma 0 square is identity. So if you do that, you can write this as U bar and then use the spin sum that we said, something that we won't prove. And with that, you can write this whole thing as this, okay? P bar plus M gamma 0. So that's where the gamma 0 comes. Px minus y, and then plus, as you will anticipate, the negative frequency have a minus M gamma 0 and x minus y. Okay. Okay. Now you can do rearranging, and ultimately you can show that just like open up this bracket as space and time, act it on this field here, and if you do all that, you can show that this finally boils down to just this, which is the definition of the Dirac delta, or the Fourier transform of identity. So indeed, taking this minus sign was crucial, and you might think where in this equation we use the minus sign, and that is precisely here. You see that this equation with a minus sign is exactly that same equation, but if you reverse the order of the dagger coming here and the non-dagger piece here, it becomes plus. And notice I had secretly used that quantity here, that there is this thing with C dagger on the left and C on the right, and there is a plus sign. So when you open this bracket, you still get the plus sign. If you write it in the other way, you will get a minus sign from there, but that minus will be cancelled by the minus that is here. So hence that's exactly where we used it, and that was crucial to proving that this indeed is true, that psi dagger indeed satisfies this. Okay, now that's fine. And we said that let us relabel the job of C and C dagger. So C dagger will now act as annihilation, C is a creation. But now let's see what's the problem is there. We understood that the minus sign was necessary to have the equal time commutator relation. But now let's see what that relabeling creates a problem. What problem does it create? So in order to do that, let us compute the Hamiltonian. And as we will see that there will be a problem in the energy of the system. Okay. So the Hamiltonian, recall, is just pi psi minus L, and it turns out that this is psi bar minus I gamma I del I plus M psi. Okay, so again do that following trick. First write that psi dagger is the momenta, and then have this identity is gamma 0 square, and then take a gamma 0, multiply it here, get psi bar, and you will see this structure coming out. Okay. Now the total energy of the system is defined as the volume integral of the Hamiltonian density. So in order to compute that, what you can first do is take the expansion of the field, the spinor field, and add this operator on it. Okay. So essentially what I'm saying is you act the uh, Dirac operator, but only the spatial indices now, on the expansion of psi, which was this. Okay. So if you act on that and use the identities that we have been using till now, then you can show that uh, this Hamiltonian, which when we derived the space-time translation, takes this form. Okay, so this comes from here directly. So this was the Hamiltonian, but now I have explicitly written out psi bar as psi dagger gamma 0. And yeah, so if you compute this in terms of the operators, uh, integral over the momentum operators, and then use this definition of the Hamiltonian energy. And here you have to use certain identities that we stated, those spinor identities. Again, this calculation is similar to this one, how we carefully did this part. So you do that carefully, and it's there in the notes. So if you do that, all of this business, what you will end up with is something like this. And it's again exactly similar to how we did in the complex scalar field. The only problem is you are dealing with spinors. So for that, you have to use these spinor identities, okay, to manipulate them. So with that, you will end up with an equation looking like this, okay? And this is something that I have typed in the notes, like explicitly the working of this. So you can look at there, but for time constraint, I won't derive it here. But we did one thing. We did some spinor identity use in the previous derivation, where we showed that the canonical commutation relations were in accordance with the ladder operator relations with a minus sign. So there we did it in detail. So I'm skipping the details here. But if you do that, you end up with this Hamiltonian in terms of the operators. Now you can use the ladder operator commutators to write this in the normal ordered form that we do, right? B PS. So all creation operators on, like all the daggers on the left, minus CPS dagger CPS plus 2 pi cube delta 3 of 0. Okay, and then we say that we neglect this, and that's fine. Okay. Okay. Now, now there will be a problem here. Some of you might already start to see what's the problem, but we will see it in detail. So note that this is what happens when you put all the creation to, all the dagger to the left and the non-dagger to the right, and you pick up this infinite energy, which we discard. So that's how we deal with this infinite energy thing. But note, we had argued that this is actually my annihilation operator, and this is my creation operator. Okay, that was necessary. And we will now see that this hence lead to a problem. So you would already start seeing, okay, there is some problem here because this is not properly normal order or something like that. So what you can do next is you can take this H. So now it's an operator. Take this expression that we are writing here, and act it on a operator B, which creates. And remember that the B's were fine. Okay, they had a nice commutator relations, and that, as you expect, will, just like the complex scalar field case, will give you back this. Similarly, if you do the H with CPS dagger, and from this Hamiltonian, you will get that it gives you EP CPS dagger. So this means that it actually raises the energy of whatever this C is doing. Okay. But now, if you do the H of CPS only, as you will expect, this will give you a decreasing in energy, as it should. But now recall that we had relabeled their job. We had said, no, CP dagger will annihilate and CPS will create. Okay, because of this pesky minus sign that was appearing. So that means what? So if I have to interpret this as creation of my excitations, then you see that when you start with the vacuum and you keep creating by acting with CPS, then you will keep lowering its energy indefinitely. And what will end up happening is that your Hamiltonian will be less than zero. So it will be unbounded below. And we know in physical system, a Hamiltonian is always positive definite. It's bounded from below. And you see, this all came up, this all problem came up because there was this issue that you can either have the minus sign or so this issue that we had, that there was this minus sign, that actually translated to having these negative energies, or the Hamiltonian being not positive definite. And now recall that the rigorous derivation that we did, that this minus sign was essential for having imposing the equal time commutator relations. Okay. Now, with this, you should be able to convince yourself that the problem was trying to impose commutator on spinors. So what then people did, they said, okay, let's forget about commutators. Let's impose anti-commutator relations now. Okay. So psi xt, psi dagger, so alpha beta. And this is just a try yet. We are not saying that we will succeed with this, but let's see. Yt is 2 pi cube delta alpha beta delta 3x minus y. So if you now impose an equal time anti-commutator relations, then you can show that for the ladder operators, you will get a relation like B. I will just write it schematically. B dagger is 2 pi cube and all the deltas, and C dagger is 2 pi q and all the deltas. Okay, so now we have that nice structure again, that everything comes with a plus sign and the commutator like B on the left and B dagger on the right, that holds, and all other things, they vanish. Okay, just like in the usual case. So these all are zeros. So with all this, now if you write down the Hamiltonian, again, the derivation will go through exactly the same way, but we will have anti-commutator relations instead of commutators. And now the energy will be, the Hamiltonian density, when integrated, giving the total energy, will be nice, as we will see. So it will turn out to be this. And so on and so, and then the vacuum energy, this delta 0. Okay. And this is in the correct way. Now these non-daggers are annihilation operators, in the sense that they create the vacuum. Sorry, they define the vacuum. They annihilate the vacuum. And so this is what will be a definition of a vacuum. And we see that everything will now work out, in the sense that if you compute H of BP, you will get minus EP of BP, and similarly H with C dagger will be plus EPC dagger, and similar relations. So everything will work out exactly how we studied in the complex scalar field case, only if we replace the commutator with anti-commutator relations. And since now we have anti-commutator relations, let's look at a two-particle example. and we will derive something which you know by the name of Pauli's exclusion principle. Okay, so a one particle state is just BPR dagger 0, right? Now imagine two particles. So P1 R1 and P2 R2 is like BP1 R1 dagger, uh, BP2 R2 dagger on the vacuum. But now these things they anti-commute. So when you flip them, you have to put a minus sign. And so you get minus P2 R2, P1 R1. So when you change the arguments in your wave function by an exchange, you pick up a minus sign. Remember in the scalar field case, because things commute, because they were commutators, not anti-commutators, so you had a plus sign here. And because of this minus sign, now you try to do something. You see that if you put P2 R2 equals P1 R1, or in other words, two particles having the same momenta and the same spin, that immediately implies that PR and so P1 R1 and P1 R1 is just 0. Okay. So this is the statement that you cannot have two fermions occupying the same, having the same quantum numbers. But for bosons or spin 0 at least that we have seen, you can do this. And this is the famous Pauli's exclusion principle. Okay. And note again something that I was telling you yesterday, that in quantum mechanics, Pauli's exclusion principle was a rule. Okay, you are told that bosons cannot integer spins cannot be kept together, and fermion the half integer spins can be, you know, they sorry, integer spin can be kept together, but half integral cannot. And all of these came as a rule. It was an extra input. But here we saw that if we did not have the anti-commutator structure, then the Hamiltonian, which at the end of the day measures energy for you, will not be positive definite. Okay, you will have an infinite tower of negative energies. The only way to remedy that we saw was to have anti-commutator instead, which meant that under exchange of arguments in your wave functions, you pick up a minus sign, unlike the bosonic exchanges. And we have also argued that you have the spin half particles in this case. So the half of spin, these particles that are called fermions. And now we see that we derive the Pauli exclusion principle. And as I was saying yesterday, all of this came from just saying that let us write down a relativistic quantum theory. Okay. Previously, the Schrodinger Heisenberg equations were non-relativistic, and hence to fit the observations in the experiments, you had to have a spin quantum number, Pauli's exclusion principle, and all this. But now we're just demanding relativistic invariance of my theory. I get all these things out. Okay. So this is what is called the spin statistics theorem, which is essentially the field theoretic version of the Pauli's exclusion principle. That if you have certain spins like integers, then they will follow commutator relations. They will satisfy commutator relations. If you have half integer spins, they will satisfy anti-commutator relations. Okay. So we saw a little bit of that. Okay. Now let's in the final 30 minutes or so discuss propagators. Okay, because we want to now understand the notion of causality and how things propagate and all this. And that is essential. Why? Because you see, we had defined causality as vanishing of a commutator. Okay, you remember that we said that if this thing was 0 outside the light cone, that is for space like points, then everything is causal. But now we are replacing commutators with anti-commutators at some specific point. So we need to check if this still holds. So for that, we need to discuss propagators. And yes, so again, you take the expressions for psi x and psi dagger x as they were written in terms of the plane wave basis in terms of the ladder operators. So I won't write down that whole expression, but you get what I'm trying to say. Okay. If you take them and if you define a quantity, so this is a definition. So the fermion propagator, I will define in this way: psi alpha x, psi beta bar y, and so instead of the commutator, we will have the anti-commutator here. Okay, and that's what my uh, spinor propagator will be. Okay, and you can now evaluate that if you plug in these values of psi's and psi alpha and psi bar beta in terms of these ladder operators, then you can show that this propagator turns out to be this expression. We will understand what this propagator does and its relation to causality. But for now, let's write down its expression. So you will see that this boils down to this. Sorry, let me be careful. This is p dot x minus y plus p bar minus m e to the power ip dot x minus y. And you again, while deriving this, you will need those spinor identities. Okay. So now you can see that you can immediately write this thing as the Klein-Gordon propagators, the real scalar field propagators. So the way to see that is if you take the Dirac operator and you act it on these quantities. So I will shortly define what these quantities are, but in the problem set, you would have already seen what these are, where these delta are just the usual propagator. Okay, so it's like phi x, phi y, where phi is a real scalar field, or in the momentum space expression, it behaves like it has this expression. Okay. Okay. So essentially what is to be done is you take this operator and you act it on these frequency solutions. And
You had a dagger on there. Delta plus dagger, phi dagger, y.
sorry, which one is phi dagger? Okay.
Delta.
Yes. That's true. If you are looking, yeah. So here, yes. So thank you. So here, this phi that I'm saying is actually a real scalar field.
Oh, okay.
Okay. But for a complex scalar field, you are right. So this comes with a dagger. Yes, nice, great observation. Yeah. But for a real scalar field, for a real scalar field, uh, this is the operator, and for complex, this just maps to phi dagger. Okay. So it turns out that if you take these ansatz, so what essentially happens is this operator acts on this minus ip dot xy and gives you this Dirac operator. So hence you can do a short exercise to show that this indeed works. I mean, the structure would be obvious from the way I've written things. Okay, but you just act. So all you have to do is act this differential operator on this ip dot x. That's what delta plus is, and delta minus of x minus y is just delta plus of y minus x, which is the propagator from y to x. Okay, so phi y to phi x. And now recall that this is something nice. Okay, why? Because you would remember from our discussions in the scalar field case that if x minus y square, that is things were space like separated, then we already know that this quantity minus delta minus x minus y, that is 0. Okay, So that we already know. And now we see that because whatever this weird propagator was in terms of anti-commutator, it actually boils down to acting with this operator on these functions. But these functions themselves, their difference vanish to zero for space-like separations. So this means what we get is this quantity x minus y actually which was these anti-commutators x and y. This is zero for space-like separations. So it means that's things are still fine. Okay, but you might say that one thing could still be puzzling to you is okay, but you see here the particle propagation was among scalar particles. What we just showed is a trick that causality still works, but at a physical level, this difference still measures scalar Klein-Gordon particles. And the trick was we could write down the propagator of these scalar Klein-Gordon particles as the propagator for the spinor particles. But can we have some commutator structure even for the spinor particles? And the answer is yes. And as you have been seeing me till now, anything that is a bit hard, I will set as an exercise. So I will not do this here. But what you can do is recall what is a scalar in the spinor language. Okay. So in the spinor language, psi bar psi is a scalar. Okay. So that means what we had in the complex scalar field case, that phi and phi dagger and their commutator vanishing for space-like separations. So that means the analogous thing in the spinor case should be psi bar psi alpha and let's say alpha and psi bar beta psi beta, and depending on x and here depending on y is 0. Okay, if x minus y is space-like separated. So because here only a bilinear makes sense, instead of a single spinor and commutator with a single spinor, we have to actually look at commutators of two bilinears. Okay, so one this bilinear and this bilinear, just like we did for the scalar field. Okay, and then the exercise is you can actually show that psi bar psi and psi bar psi, so depending on x and depending on y, is actually related uh, linearly to these anti-commutators of psi and psi bar. So this is a very powerful statement that anti-commutator of the spinners themselves is related to the commutator between spinor bilinears or Dirac bilinears. Okay, so this is something that you can show, and it's very simple to show, but a bit tedious actually. So it's not at all difficult. You only need two commutator identities, and these are again something which are easy to uh, understand. So you can show that take any matrix A and B, the anti-commutator and the commutator are related this way. So that's first identity. The second identity that you will need is ABC is ABC plus ACB, and the third thing is ACD is ACD plus uh, CAD. Okay. So in other words, you always have to preserve the ordering. So that's why let me just briefly explain what is going on here. So you see there is A and B are multiplied and then taken a commutator with C. So the ordering A, B should be preserved, and also that C acts from this way. So that's why when you expand this out using distributive property, the commutator distributes as B, C, and A remains on the outside here because that's how A acts on B and C. And since B was acting on A from the right, that's why B goes all the way to the end, and it first comes A and C, the commutator of AC. Similarly, here also, you take AC commutator first and D goes to the far right. And if you do A and D, then C will go to the far left to preserve the ordering. Okay, because these are in general matrices or linear operators. So with this, you will be able to show that indeed the commutators between bilinears, because only a bilinear is a scalar, vanishes, and hence having this notion of causality is still fine. So the trick that we got by using the Klein-Gordon was actually not a trick. There is much physics behind it, and the physics is in this relation. Okay. Now, the final part of this today's lecture is, let us discuss briefly what's the Feynman propagator and time ordering. Okay. So for that we need two different 2-point functions. And again, using the ladder operator expressions, you can show these things. So P plus M and e to the power minus that thing, and psi beta bar y psi alpha x equals d3p by 2 pi q, the same energy factor, but now the opposite Dirac thing acting on the plus. Okay, so when we have these things, we define the Feynman propagator SF x minus y as the time ordered thing, sorry, the time ordered psi x psi bar y. Okay, and what is this time ordering does? So this gives us 0 psi x psi bar y acting on vacuum, and minus psi bar y psi x 0. Okay, the first thing when x0 is greater than y0, and the second thing y0 greater than x0. So recall the Heaviside step function, and that's what time ordering means. And now note that this minus sign comes because psi, so when you take psi x and psi bar y and you say that you want to time order them, so you have to flip psi bar y to the left of psi x, right? In the bosonic case, it was just this much. So that was for the boson. But now you will pick up a minus sign when you take psi to the left of psi, psi bar to the left of psi. And hence this minus sign appears. Okay. Because time ordering just says that exchange the fields. But we know that here they are anti-commuting. So if you exchange, you pick up a minus sign. And succinctly, compactly, let's say, we can write just like we did for the complex scalar field case. And we can then stare at it that it will be very similar to the complex scalar field equation for the Feynman propagator, and it turns out to be like this. The only difference that you will be noticing is that in the numerator, now we have the Dirac operator in the momentum space, but in the complex scalar field case, this was just 1. Okay, so we just had 1 over p square minus m square I epsilon. But now we have the Dirac operator acting on the plane wave basis. And you can show, just like the complex scalar field case, that if you act it with the Dirac equation, you would get the delta source. So remember that the complex scalar field case, the Feynman propagator solved the Klein-Gordon equation, which was the equation of motion in that case, but with a delta source. Here also it solves the equation of motion, which is the Dirac equation here, but with a delta source. And now if you remember that we then discussed something like on shell and off shell particles. So we said off shell particles are things, sorry, not off shell and on shell particles, but particles that are on shell and particles that are not on shell. So we said the former is like the real particles and these are virtual particles. And the complex scalar field Feynman propagator, it propagates what are called virtual particles, as you will see like in next week when you will be taught interacting theories. So here also this Feynman propagator will carry virtual but fermion particles, not virtual scalar particles like in the previous case. And that is the essence of this equation, that it doesn't solve exactly the equation of motion, but the equation of motion with a source. And then we had this argument that things are on shell and off shell, these kind of things. Okay. Uh, so yes, so I think that is it. Let me check if there is anything else that I'm forgetting. No, I think that's it. So actually, let's. So that's what I had to convey to you in the last lecture, and so it might be that we did things quite in a rush way for the quantization and everything, because we were a little short in time today. So that's why, and also this was the last lecture, but I wanted to give you the flavor so that when you, at least when you look at these equations, like when you look at the Feynman propagator for the Dirac field, then you can compare it to the complex scalar field propagator, Feynman propagator, and we could see what are structurally the differences. Okay, and what similarities are there. Like the similarity is in this equation, that the Feynman propagator still is a equation of motion satisfying object, but with a source. Okay, so it satisfies the inhomogeneous equations because it now comes with a source. So in this way, you can at least see that when we discuss scalar particles, and then we also have now briefly discussed spinor particles and their equations, which of the structure remains the same, which of the structure they change, and all this. And so that's why, even though things were a bit rushed, I wanted to convey these things to you. But because they were rushed, so in the exam that you will have at the end, you will not be given anything about the Dirac quantization part. You will only be tested till the classical Dirac field theory, which involved the Lorentz transformation, parity, and all these things. So I won't set any questions from the quantization of Dirac part. Okay. And yeah, because it involved these spinor identities and all these things, which we again didn't prove in class. So, and also we rushed through all these things a bit fast. So you will not be graded on this, and also you won't be given any assignments on them. Okay, so all the assignments and everything regarding grades and marks will be only till classical Dirac field theory. Okay, so now let me end today's lecture by saying that by giving a brief summary of what we learned in these 6 lectures. So you see, our goal was to,
So, sir, that's the syllabus will be before the quantization of Dirac fields.
yes, the syllabus for the assignments and for the exams will be till chapter 7 in the notes, which ends with classical Dirac theory.
Okay.
Yeah.
Thank
So,
you.
so our goal was to study relativistic field theory. Okay. So I will take like 5 more minutes of you and then I'll stop. And that goal came about because we wanted to create an harmony between special relativity and quantum mechanics. And we saw that continuous degrees of freedom, they emerge, there are infinite degrees of freedom and all that. Okay. So that was the goal. How much of that goal have we achieved? So in all our discussions, we have only studied free theories, what are called free theories. Okay. So free theories means non-interacting. Uh, okay. So that's why, for instance, in the scalar case, the potential that we took was just this half m square phi square potential. And we had shown that in the momentum space, this means that uh, each oscillator mode K satisfies its own SHO and they are decoupled. So there are free theories. So these are free theories. They don't interact with each other. And we saw spin 0 and spin half particles. Like, okay. So even if things were non-interacting and they were essentially free, still we could learn many concepts about QFT, like bosons can come together, fermions have to have different quantum numbers, which was Pauli's exclusion principle. Then the idea of spin and how to use Lorentz invariance to constrain many things, and how Lorentz invariance gives you all these nice qualities. So all this we could learn only by studying free theories. Okay. But unfortunately, nature is not really free. So nature is very interacting. So we have only completed part A. So in part B, you will next move on to understanding interacting QFTs. Okay. So I guess your first thing would be to add interactions on top of the simple harmonic potential. So you will study something like lambda phi 4. Okay, I think it's 4 factorial. Yes. So this term is an interaction term which will now lead to coupling of your oscillators. So it will not be a free theory, and hence you will see that you won't be able to solve the theory. Okay, like remember, we were able to solve the theory because here each simple harmonic oscillator was decoupled, and we know how to solve a simple harmonic oscillator differential equation. So we used that to find out the plane wave basis, and then we went forward and we quantized, everything worked out. But here things will not work out. So how do you solve this then? The way to solve this will be what we'll call a perturbative way. Okay. So some of you who would have taken advanced quantum mechanics, you would have seen that there is a perturbation theory where you treat this parameter lambda as a small parameter, and then you will perturb your theory around it. So you will be able to solve certain things there. Okay. Uh, Additionally, so once you complete this course, you would have completed understanding what is perturbative QFT. Okay. And another thing is, from the point of view of symmetries, we looked at the E1 symmetry that acted on the spinners in this way. Now later you will look at SU2 symmetries, sorry, SU3 symmetries when you will study standard model. And also you will look at U1 in from the lens of gauge symmetries. Okay, so you will learn what is gauge symmetries, and then you will learn all these things. And then you recall that we made a remark yesterday that elementary particles are nothing but different unitary representations of your Poincare group. Okay, so having on top of Lorentz and Poincare symmetry, if you have other symmetries like this, then that also restricts what kind of representations you will have and what kind of transformations particles will obey, because elementary particles are like representations of your symmetric group. So if you just have Lorentz symmetry, then that's the only group that you have. But now you have other symmetries like U1 and all these things. So you will learn these things in detail. Yes. And the last thing that's there that probably you might not learn, but you should know, is, you see here we said that all of this comes under the name of perturbative QFT because things are strongly coupled, they are not decoupled, so we have to expand them. That phenomenon, that part of QFT is called non-perturbative QFT. Okay, where things are quite exact and you don't need to rely on these perturbation techniques. We actually saw one glimpse of this even in the free theory, and that's why I'm talking about this. So the term that we called anomaly is actually a non-perturbative phenomena. Now this is something you have to take from me. There is no way that I'll be able to convey this in the next 2 minutes, but I'm just saying even the free theory is so powerful that it already shows you something that is there in this richer corner of non-perturbative QFT. Okay, you would have heard these buzzwords. So these are buzzwords in physics, some of the buzzwords. like instantons and solitons. So these are all comes under the umbrella of non-perturbative QFT where things are exact. Okay. So, but I think this whole school will be only about perturbative QFT. That's how one learns QFT first. That's how QFT was discovered, and that will teach you many more things. So, so one last thing is there could be some typos in my typed notes, like a minus sign or a plus sign here and there, or some phase differences. So one request to all of you would be to please let me know if you find those typos, uh, because as you know, different people have different QFT conventions. So my lecture notes are based on many lecture notes and books. So different books and notes, they have their own things. So I have to translate them in a unique way. Sorry, in a comprehensive way. So I might have missed a sign here and there. So if your answer doesn't matches my answer by a factor of plus or minus, then definitely I have done some error and let me know. And so that will be my only request to you when you are reading the lecture notes. And thanks again, everyone, for giving me this opportunity to teach you. It was a great learning experience for me too. I also learned many things, even in QFT. As I said, I keep learning. So it was like it's great to have you all, and it was really enriching. Yeah, I think I should stop speaking now. And if you have any questions regarding today's class or anything in general, I can take them. Okay, one more thing. So my lectures are ending today, but this I will be available in Slack throughout the whole course, like till you end the course with other lecturers. So and when your exams are graded, everything. So if you have doubt, you can post them in Slack, and I'll keep answering them. Okay. So I'll be available in Slack throughout the school. How many marks are allotted for the final exam and assignment? Oh, okay. I don't know how many marks are allotted. Maybe the organizers are still deciding that. Uh, so Mishal, there's a question